To introduce this next section, I'm going to pose a question. Can we do negative work? Can an object have negative work done on it? The answer, well, let's start with our equation. FD cosine theta FD cosine theta suggests that we can, because if theta is greater than 90 degrees, cosine theta is negative. So we could imagine getting a negative number out of this. And in fact, that is true. We can have numbers that are given as negative values. Let's take an extreme case where we have, I don't know, a wagon or some cart moving to the right. So the velocity is this way, or in other words, the distance this thing is going to move is also to the right. And we have a person, I guess I'll put them over here, pulling on this maybe just so they're out of the way. We could have them pushing on this side with a force to the left, but just so this is easier, I'll have them kind of frantically trying to stop the cart by pulling on it and exerting a force that way. So I said frantically trying to stop the cart because that's the only reason we would be pulling on the back of it, but in fact it turns out that that is important. That plays into what's happening here. So our force and our direction of motion are exactly opposite, which means theta is equal to 180 degrees. The cosine of 180 degrees is -1. So our work here is equal to minus F times d. So we are definitely doing negative work on our object. Now in this case, our velocity is to the right, our direction of travel is to the right, our force is to the left. So if this is the only force on our cart, this force is going to cause an acceleration to the left, right? And our acceleration and our velocity are in opposite directions, which means this force is acting to slow down the cart. Contrast that with our example from before of the person pulling the wagon, right? And here, if they're exerting a force to the right and going to the right, then if this force is the only force, again, the acceleration is also going to be to the right. And if acceleration and velocity are in the same direction, this speeds up. I put a question mark there because there could be other forces, but as long as this is the only force, these are both true. So, in other words, positive works are going to tend to speed things up. Negative work is going to tend to slow the objects down. So that's the first kind of rule that's going to come from our work. And we could have multiple forces complicating this, but if we're just looking at one force at a time, this is the rule that we get. So, as an example, let's look at the work done by one of our favorite forces, friction. So if we have a surface and we have a block that starts with some velocity on the surface, it's sliding, but there is some friction, mu equals 0.4 or whatever, the number doesn't matter for our example here. So this velocity is to the right. We know our force of friction is going to oppose the velocity, so our kinetic friction force is going to be to the left. And with these in opposite directions, the block is going to slow down. In fact, we know that friction is always going to be opposite the direction of motion, and therefore the work done by friction is always going to be negative. So our friction force can only act to slow things down. We can't drop a block on the surface and wait and expect the friction to push it and get it moving, because that's not how friction works. So the friction work is always going to be negative. Okay, so the next part I want to talk about is where is this work coming from and where is this work going? So when we were talking about the effort required to do work, pull the wagon, push the truck, whatever, you cannot do that indefinitely. Like something is getting used up as you pull on the wagon for a distance. So something about the thing doing the work is different. Similarly, the thing that the work is done to, the wagon, is also different. You could, it could be in a different place. You could have pulled it up a big hill, or maybe if you're on flat ground, you can do work and get it going really fast. And so work has the potential to change the motion or some other kinematic properties of these objects. So there's some connection between work and kinematics, and that is where we will start our understanding of energy. So energy is kind of tough to define. It is a quantity that is conserved. So you can change forms of energy, but you can't, create or destroy it. And there are lots of different forms of energy, right? There's chemical energy, there's nuclear energy, there is energy in rays of light, there is energy in your candy bar, and there is energy in the motion of objects. And so there's energy related to our kinematics that we've learned and the forces that we've learned also. So work, it turns out, in this context of energy, regardless of what type of energy we're talking about, work represents a transfer of energy. Not all transfers of energy are work, but all work is a transfer of some sort of energy. So this, in the process, changes the energy of the thing doing the pushing, I guess we'll call that the pusher, and the thing that is pushed, the object, right? So if I push on the block, that costs me energy, but the block speeds up, right? It goes faster, and that represents a transfer of energy from me to the block. So energy is conserved, like we said. Might as well write that down. Conserved in physics means, can't be created or destroyed. And the conservation of energy is another one of those real hard rules that physicists believe is true always, everywhere in the universe. You can be nitpicky and say, well, you can destroy mass and turn it into energy, but mass is really just another form of energy, really, if you keep digging. So we won't get into the nuclear physics of that. And energy is going to have the same units as work, in case you didn't already knew that. Our units of energy are joules also. No surprise there. Okay, so we said we can transfer energy from me pushing a block to the motion of the block, the block gets energy. And whatever's going on with me is a complicated biomechanical, chemical mess that's, beyond physics 106, but a mass moving at some velocity, we definitely have the tools to describe the energy of that. So any object undergoing motion, so any object with velocity is going to have energy associated with that velocity, and that is the kinetic energy. So kinetic here, like the word kinematics, this means motion or movement. So kinetic energy is the energy of the motion of an object, by virtue of nothing more than the fact that the object is moving and the object has mass. Okay, so our variable for kinetic energy, the book uses a capital K. Sometimes I try to use K, sometimes I forget and use KE for kinetic energy. This is still just one variable with two letters. So sorry if I switch back and forth between those. And so we'll stick with K as best we can. And our equation for the kinetic energy of an object is 1/2 mv squared. So 1/2, we know, m is the mass of the object, and v is the velocity of the object squared. So things we can notice about this, v squared is always going to be positive. We can have situations where our amount of energy is negative, and we will run into that eventually, but kinetic energy is not that. Kinetic energy always has to be greater than zero. The lowest kinetic energy you can have is 0 when you are, standing completely still. Our kinetic energy does not care about the direction of v. Also, if v is in the plus x or the minus x or up or at some angle, it doesn't care. It's just v squared, and this v is like the magnitude of our velocity vector. So if we have some velocity at some angle with an x component and a y component, it's the hypotenuse that we're interested in this equation. It turns out you can find the x energy and the y energy and add them up, and you will get the same answer. But I think it's better to think about the total speed as what's going into that equation. All right. So the last thing I want to say about kinetic energy is if we have a system with multiple parts, so say instead of one block moving on the table, we have 2 blocks moving on the table, or we have, a bunch of balls that are all thrown at once. The kinetic energy of that system of objects is just the sum of the kinetic energies of the pieces of the object. So the kinetic energy of the system is just the sum of the kinetic energies of the parts of the system. So there will be points where we're trying to find out, total, all these objects taken together, how much kinetic energy do they have, and we will see that we just add up the kinetic energies. If we have objects moving in opposite directions, like a ball going this way and a ball going this way, and this is like V1 and this is V2, the fact that these are going in opposite directions doesn't matter because the kinetic energy totally doesn't care about the direction. So it's still 1/2 m that v squared plus 1/2 m that v squared. The fact that these are opposite does not matter at all. All right. So this is what happens when we do work on an object. Doing work on an object puts energy into the kinetic energy of that object. And we have a very succinct way of summing up this relationship, which we will very quickly write down, called the work energy theorem. And that is, if we have an object with work done on it, so the work done on some object could be coming from multiple forces. So there could be different forces doing different amounts of work on the object. Maybe some are positive, maybe some are negative. And when we add those all up, we get the net work on the object. So this is the sum of all positive and negative work. The net work done on the object is equal to the change in the kinetic energy, of that object. Which is pretty much what we said, right? If we do work on an object, we are increasing its kinetic energy by the number of joules of work that we do. The only difference here is that this is, we could have multiple forces doing multiple different amounts of work. And more on how to calculate the net work with multiple forces coming up later on. To close this video out, I just wanted to paint a picture of where we are now in physics. So if we have forces on objects, this is kind of a thought picture thing I'm going to do. If we have forces on objects, we know from Newton's laws that we can use those to find accelerations, right? This arrow represents Newton's second law, right? So the forces cause accelerations, and the accelerations cause changes in velocity, and these can tell us how the motion of an object changes, right? This is just kinematics happening here. Now we have learned that we can also use forces to find out the amount of work done on objects, and with the work energy theorem, we can use this work to see the change in their kinetic energy. And a change in kinetic energy is related to a change in velocity. So these pictures over here on the right are not so different. This is the work energy theorem there. So we have these two different paths the first one we've done a lot in chapters 3 and 4. This path is what we are going to do in chapters 5 and to some degree 6 or 7. We're going to add some other pieces to this. And these are equally true, and they are both totally useful in different situations. And if there's a situation when we can solve a problem with either one, they should give a consistent answer. So as we will see, if we can do that, if we are equally allowed to figure out accelerations and velocities or figure out works and kinetic energies, and there's nothing missing from either one of those pictures, we'll get exactly the same answer over there at the end. So that's kind of neat that these equations are consistent with themselves, and in some cases, the approach you take to solve a problem is totally up to you, and can be obtained through several different paths.